Do you get lost in complex GRE rate questions? I know I did, at least until I started using this trick. I'm Erika with Target Test Prep, and today I want to share a wildly underrated trick for GRE rate questions, and then we'll apply that trick in 4 different types of rate problems from the Target Test Prep course. This move requires a somewhat advanced understanding of rate principles, but not so advanced that you won't understand it by the end of this video. If you've seen my video on 3 levels of work rate, you know that at the core of work rate problems are 2 equations. Our classic work rate formula, W equals RT, or work equals rate times time, and our combined rate formula, R sub A plus R sub B equals R sub A and B, or the rate of A working alone plus the rate of B working alone equals the rate of A and B working together. When we do distance rate problems, we regularly use the distance equivalent of the first formula, D equals R times T, or distance equals rate times time. Distance is the work being accomplished when something moves, so this makes sense. What I don't often see is the second combined rate equation being used for distance problems, but it can be. And using it radically speeds up and simplifies some of the most complex problems on the test. We're talking diverging rates, where 2 things are moving away from each other. Converging rates, where 2 things are moving toward each other. Catch-up rates, where one thing is either gaining on or falling behind another object. And relative rates, where an outside force is changing the speed of another moving thing, and where that outside force can either be working with or against the thing that was already moving. These problems can be time-consuming and error-prone. I'm going to show you how to solve them quickly and with high accuracy. Let's start with a diverging rates question as a warm-up. All right, pause the video if you want to give this one a try on your own. We'll solve this one the standard way first as a point of comparison. All right, standard method to solve here is to set up one equation for Will and one equation for Carly. Now, because I'm going to have multiple equations here, I'm going to set up a rate table to stay organized. So distance equals rate times time. All right, starting with Will. Well, we know that Will is traveling 12 miles per hour, so that is his rate. But that's really all we know. We know that Will and Carly together travel 66 miles, but we don't know how much of that is Will's individual distance. And then time is what we're solving for. So we can fill in D sub W or D sub Will for our distance, and we can fill in T for time. And we'll talk about why we chose those specific variables in a second. Okay, moving on to Carly. We know that Carly is traveling 10 miles per hour, but again, we don't know much beyond that. So we'll fill in D sub C or D sub Carly for distance. Using this subscript to designate that D sub W and D sub C, Will and Carly's distances, are not equivalent values. But because Will and Carly should have the same time, we can simply fill in T for time to designate that those are the same. So this gives us 2 new equations. D sub W equals 12 times T, and D sub C equals 10 times T. Okay, but at this point, there is still more information that needs processing. We know that Will and Carly end up 66 miles apart, so we can use our previously defined variables for distance to build a new equation for total distance. So D sub W plus D sub C equals 66. All right, we have 3 equations and 3 variables, which means we should be able to solve. Now, plugging our first 2 equations into our third equation, we get 12t plus 10t equals 66. Adding, we're going to get 22t equals 66. Dividing both sides by 22, we get t equals 3. Now, we've been working with miles and miles per hour, so this answer is in hours, but we are looking for the answer in minutes. So multiplying by 60 gives us 180 minutes, or answer choice D. Now, this isn't too bad. Sure, it's several equations, several variables, but it's all pretty simple. But let's try the combined rate method. All right, thinking about Will and Carly as working together to move away from each other. In distance equals rate times time, Their combined distance is 66. Their combined rate is going to be the rate of Will plus the rate of Carly, or 12 plus 10. And then their shared time is what we are solving for. All right, adding, that gives us 66 equals 22 times t. And you'll notice that this is where we got to all the way down here in our previous method. So by using this combined rate method, we skipped all of this extra work. And as before, from here, we will divide by 22 to get t equals 3 hours, and then converting into minutes, 180 minutes. Answer choice D. Done. So this method is one, obviously much faster, and two, because it has fewer elements, less error prone. Every additional equation, every additional variable is an opportunity to make a mistake. In this second method, there is so little work that making a mistake would be difficult. Let's try a similar problem around converging rates, and then we'll get into some of the weirder rate question types. Again, pause if you want to try on your own. We'll do the standard method first. Setting up our rate table to get us started, distance equals rate times time, with rows for plane A and plane B. Okay, in this problem, we know that time for both planes is 2. Great. Now, we know that one plane travels 60 miles per hour faster than the other plane. We don't know which one, but it turns out that it doesn't matter for this problem since we're solving for the sum of the rates of the planes. So we're going to go ahead and decide that plane A flies at r sub A, and that plane B is the one that flies 60 miles per hour faster, and we'll set the rate of B to r sub A plus 60. And then once again, we don't know the individual distances of each plane, so we're going to go ahead and set those to d sub A and d sub B. So that is 2 new equations. Okay, like the last problem, we know combined distance. The only difference here is that in the last problem, our elements were diverging or moving away from each other, while here they are converging or moving toward each other. But regardless, they are covering a combined amount of ground. So here combined distance is 840 miles. So we're going to build a third equation using our previously set distance variables. So d sub A plus d sub B equals 840. All right, plugging in and slightly rearranging, we're going to get 2 times r sub A plus 2 times, in parentheses, important, r sub A plus 60 equals 840. All right, expanding that, we're going to get 2r sub A plus 2r sub A plus 120, remember to distribute correctly, equals 840. Okay, combining like terms, we are going to get 4r sub A equals 720. Dividing both sides by 4, we're going to get r sub A equals 180. But that is not the answer. We are not solving for the rate of A. We are solving for the sum of the rates of the planes. Careful. So we are looking for r sub A plus r sub A plus 60. So building that little equation and plugging in our value for r sub A, we get 180 plus 180 plus 60, or 420. Answer choice D. So, kind of painful, huge potential for error. Let's try the combined rate method. In distance equals rate times time, the combined distance is 840. The shared time is 2. And if we look critically at our question target, we'll notice that the combined rate is actually what we're solving for, the sum of the individual rates of the planes. Divide both sides by 2, and we get that the combined rate of the two planes is 420. Answer choice D. It's that simple. We didn't need any of this information about how one plane is 60 miles per hour faster than the other plane. We didn't need to do all of this work. We didn't need to subject ourselves to the potential to make an enormous mistake. What we thought was a trap, solving for the sum of the rates of the planes, was actually a hint at how to approach the problem, solving for the combined rates of the planes. So by looking critically at what we're solving for and utilizing the combined rate method, we can solve extremely simply and save ourselves from wasted time and wrong answers. The next problem is a catch-up problem, and it introduces a little more complexity. Pause again if you want to try this one solo. Once again, we will start with the standard method and setting up our rate table. All right, rate is going to be easiest to fill in. Tom is 8 miles per hour and Chandra is 12 miles per hour. Now, time we do not know, but we know that Tom runs for half an hour longer than Chandra because he starts half an hour earlier. So we can set Chandra's time as T and we can set Tom's time as T plus 1/2. And then T, or Chandra's time, is what we are solving for. How long will it take for Chandra to catch up to Tom? And then distance, we also don't know, but since we know that they are starting and ending in the same place, we know that Tom and Chandra's distances are the same. So we can set both of these as D. So this gives us two equations that are equal to D. And because of this, we can set them equal to each other. So we have 8 times, in parentheses, T plus 1/2 equals 12T. Expanding the left side by distributing, we get 8T plus 4 equals 12T. Subtracting 8T from both sides, we get 4 equals 4T. And then dividing both sides by 4, we get 1 equals T, or answer choice C. So this really wasn't so bad, but let's go ahead and take a look at combined rate as an alternative. With this method, we're going to take the problem in stages, much like we would with a multi-stage combined work rate problem. And because I have multiple stages, I'm going to set up a rate table here as well. All right, in our first stage, Tom is running alone. When Tom is running alone, his rate is 8 miles per hour, and his time running alone is 1/2, that half hour he runs before Chandra starts. This tells us that our distance is going to be the rate times the time, or 4. All right, at this point, Chandra starts running, and they are running together. Now, this is the important part. These 4 miles that Tom ran alone are the distance that Chandra needs to make up. Yes, Tom is going to keep running extra miles that Chandra is going to need to run too, but the work that is being accomplished while they are running together is catching up on that 4-mile difference. So the distance for our together row will be 4. Okay, now this is the second important part. For converging or diverging questions, our two elements are working with each other to move either together or apart, which means that we add those rates together. For catch-up questions like this one, our elements are actively working against each other. As established, Tom is continuing to run away from Chandra, gaining distance at 8 miles per hour. So Chandra needs to run at 8 miles per hour just to keep pace. It's the speed she runs on top of that 8 miles per hour that helps her close that 4-mile gap. So to find this, instead of adding the rates, we're going to subtract them. So the speed for this row is going to be Chandra's rate, or 12 miles per hour, minus Tom's rate, or 8 miles per hour, for 4 miles per hour. And then T is what we are solving for. So pulling this equation out, we get 4 equals 4T. Divide both sides by 4, and we get 1 equals T, or answer choice C. So, leaving out all of the extra explanation that I did, is this much faster or much less work than the standard method. For this problem, maybe a little bit, but not a huge amount. But if we already have a handle on multi-stage work problems and are used to that process, which we should be for the test, this approach can be more intuitive, more logical, and overall simpler than the other method. It's worth noting that we can also have multi-stage convergence and divergence problems so long as one of the elements starts moving toward or away from the other element before that other element starts moving. So in these cases, we would combine our approaches, setting up a table as in the last problem to organize our work, but adding the rates as in the first two problems since the elements are working together. Here's an example problem if you want to give that a try. Leave a comment with your answer if you do. Last up is relative rate. Now, this is the only type of distance rate question that I do typically see solved with the combined rate method, so we'll jump straight in with that approach. As always, pause the video if you want to try this one independently. In this problem, we have two stages, moving with the walkway and moving against the walkway. Because we have multiple stages, like in the last problem, we are going to set up a rate table. Each stage in our table will cover 350 feet, or the length of the walkway. Now, in the first stage, our walkway is working with the child, so we are going to add the rates. 2 feet per second plus 1.5 feet per second is going to be 3.5 feet per second. In the second stage, the walkway is working against the child, so we will subtract the rates. 2 feet per second minus 1.5 feet per second is 0.5 feet per second. Now, the times for each stage will be different, so we'll call those T sub W for with and T sub A for against. Now, importantly, looking at our question stem, we can see that we are solving for the total time, the time it takes to go with the walkway to the endpoint, and then against the walkway back to the starting point. So we are solving for T sub W plus T sub A. Okay, taking our first equation and rearranging it, we get T sub W equals 350 over 3.5, or 100 seconds. Doing the same thing to our second equation, we get T sub A equals 350 over 0.5, or 700. Now, again, note that this is not the answer. We are not solving for T sub A. We're solving for the total time. So taking these values and plugging it into our little expression here, we get 100 plus 700 equals 800 seconds of total time. And the answer is E. So which method do you prefer? Standard or combined rate? Or do you prefer different methods for different problem types? I'm curious, so let me know in the comments. And if this video helped you, give it a like and subscribe for more content like it. Thanks for watching, and I'll see you in the next one.